Good evening. It's time for one more lecture that builds a little bit off the quantum mechanics one, but mostly is a standalone lecture that's going to be about a technique that you're going to use in the lab. If you look at the lab schedule, about 4 or 5 weeks are dedicated to 2 lab reports on one topic, which is surface plasmon resonance. Surface plasmon resonance is sort of the generic name for the technique, and the instrument maker, there are a ton of them, but one of the prominent instrument makers is the Biacore instrument. And this is the instrument that I learned to use way back before my first boy was born, so I can tell you that was more than 16 years ago now. And I learned how surface plasmon resonance worked in the sense that I could use the instrument, but I didn't really know what was behind it. I didn't know how it worked, even what a plasmon really was. And so when I started teaching this technique, I realized I wanted to learn all the things I didn't know. And so I learned them, and I am going to tell you about them now. And so at the end of this, you'll actually have a deeper connection to the physical chemistry of SPR than most people who actually use SPR and Biacore instrumentation and things like that. You'll have a firmer grounding than most of those people. And so, who knows, maybe someday you'll be working for a job and they will be looking for somebody to explain what's going on with the SPR machine, and you'll be able to do it, or you'll be able to look this up and give it to them. I'll make it available on YouTube too. All right, so the thing is, there's 3 parts that we're going to talk about. We're going to talk about like the basic physics behind it in part 1. Part 2, we're going to talk about the instrument itself. And part 3, we're going to talk about the experiment that you're going to do. So let's get on to the part 1 experiment, and there's actually some basic physics going on right here with surface plasmon resonance techniques. And it comes down to the question, it also explains the question, why is gold yellow? Now that might seem kind of surprising, but the answer to that actually has to do with its plasmons and the way that they absorb light energy. They absorb the other colors, and so yellow gets reflected. And I'll explain what that means and how that works. So surface plasmon resonance has to do with light hitting a gold surface, and it has to do with the what's called the total internal reflection. And what's the total internal reflection that happens when you have the gold surface? Well, it's a special form of refraction. So let's start all the way back with the physics of refraction. Refraction is when light is bent by moving from one medium to another. You might be familiar with this from like glasses of water or swimming pools or things like that. You can actually see it in all sorts of places, even here on this close-up picture of Venus crossing across the sun. If you look really carefully at this, you know, you have Venus right here blocking out the sunlight. If you look at this arc right here, that arc is going to actually lit up yellow with the sunlight being passing through it. But the sun's not actually behind that. The sunlight is actually hitting the backside of Venus, and it's coming around the planet, and it's being refracted by the atmosphere. It's bouncing around inside the atmosphere, then it bounces out the other side, and we see that as a yellow color to Venus's atmosphere. So you can see that Venus has a pretty thick atmosphere. The fact that you can see it at this level at all means that it's pretty thick. But it's refracting the sunlight, and that tells us we can use the light energy to tell us about what's in the atmosphere, what's going on inside it, what kind of chemicals are in it. So Venus's atmosphere is bending the sunlight through itself, and it comes bent around the planet through the atmosphere. That's the refraction bending of light. Here's another example, a little bit closer to home. I believe this is Yosemite. This is not a doctored photo from what I believe, at least I believe that it could be real, that you have the moonrise rising over the waterfall, and you see right here you have the moonlight being refracted through the water of the waterfall. You see it's being bent through the water, and then it comes out the other side, and we can see it coming out the other side. So in the way, the water is actually acting as a wire for light, and that's one of the ways that actually fiber optics work. They actually have their wires for light that they work because they refract and reflect the light through them. So refraction is the bending of light, and here's something else to notice about refraction. There's actually, if you're underneath and you're in the more dense medium, at some point the light gets bent so much that it reflects back on itself. And so you see at the very top of this picture, you're underwater looking out, and you can see the rest of the outside of the pool here. But, and this is the place where the light is just getting bent, but it's still coming through. You can even see that the light is kind of bent here because this doesn't really match up with the steps under the pool. But what's really cool about this is that you can see that there's a certain angle where you go from just bending the light to entirely reflecting the light. The light turns into a mirror up here above the stairs. And so there's a certain angle that's called the critical angle, where you move from just bending the light, refraction at the top, to actually bending the light back on itself so it bounces back at you, and that is reflection. And that's the part on the bottom right here. This is where it's acting like a mirror. And so what is going on here? Well, it has to do with the fact that the light is bouncing around, refraction bends the light, and at a certain point you bend the light so much that it bounces back on itself. It has to do with the angle at which the light is refracted. And so here's an example that we could do. You can fill a 2-liter bottle with water, and you can shine a powerful laser through it. The laser light is all in one row, but you can see the laser light very clearly bouncing off the bottom of this, and it's refracting, it's being bent, so that's a form of refraction, but it's refracting so much that it's reflecting. It's actually bouncing off of the bottom of this like a mirror. This is not a reflective surface at all. This is actually something having to do with the light itself being bent. And so you can actually see a water bending laser light if you in another really cool demo that you can go back and you can watch, and I'll try to post this online. I'll show you what it looks like right here. This is the YouTube video that is bending the light using water, and it's an experiment using the laser. You basically have a water bottle that you poke a hole in so that the liquid pours out through this hole, and if you shine the laser off to the side here, the laser, if you hit the hole just exactly, you can see that the green laser light gets bent along with the water. The light should be going straight, right? But instead you see it's bending down and it's following the path of the water. The water itself is acting like a refractive wire. It's like a fiber optics wire, actually. It just happens to be liquid rather than solid. And so this is another example of the refraction where you have it bent, the light is bent so much it's actually gone from refraction to reflection. And you have the light being reflecting off the sides of the water, and it travels along the path that you have right there. So back to our presentation, there's actually a lot of cases where you've seen things like refraction and total internal reflection. If you've ever looked at a friend's ring, and that friend's ring is really sparkly, the sparkles come from the light being refracted and reflected inside the gem. And in fact, the facets are designed to help accentuate this effect. So here's one of the highest refractive index materials. Refractive index is how much does the light get bent when it passes from one medium to another. And so diamond has a very high refractive index relative to air, and the result of that is that the light will bounce around and it will come out as slightly rainbow colored but very sparkly and very pretty, and worth a lot of money apparently. Diamonds sparkle because the light goes in, it bounces around like the light inside Venus's atmosphere, like the light inside of that water bottle that we showed you with the laser. And the dense carbon matrix that is the diamond has a refractive index of 2.4, which is really high. Most things are around 1 or so. The interesting thing, cubic zirconias are another material with a high refractive index, and that is why they can be used as imitation diamonds, because they bounce light around almost as much as a diamond does. I wonder how close you have to look to be able to tell if the bouncing light is a refractive index of 2.4, therefore a diamond, or a 2.1, which is a cubic zirconia. And certainly there's a test you can do, but I wonder if you can see it by eye, or if really cubic zirconias are not distinguishable from diamonds by the average person. So there's another example. Have I mentioned the Exploratorium yet? If I haven't, I will mention it again in this class. The Exploratorium is in San Francisco, one of my favorite places. My boys went there with me, and we explored And they have a lot of, they make their own science exhibits. So there's a lot of science exhibits there that are nowhere else. And there's examples of refraction that they have. And so I'd like to show you this movie, which is a table that they have with a Golden Gate Bridge, but you see that the Golden Gate Bridge is broken. They shifted the picture so that you can, so that the bridge looks broken. Well, can we fix it? Well, they give you something with a high refractive index that will bend the light so that it will appear to fix the bridge. So here is the example. Here's the refractive index material. You turn it to get the right angle, and when you turn it at the right angle, oh look, the bridge is now fixed. Notice that the bridge is actually at two different levels. You haven't changed the bridge itself. You've just changed the way the light passes through. And here's another thing you can fix. You can twist to fix this particular sort of prismatic type pattern that they have right here. And so that's the really cool thing that, that they have. And that just shows you thick, transparent materials will bend light. Okay. Well, why does light bend? Why does it refract? And the answer actually has something to do with calculus. Okay? So you know I have to bring calculus into all of these lectures at least one point. And so here's our point for this lecture. It's really kind of an interesting thing about light, that light, when it takes the refractive index path, when it's bent according to the refractive index, the light is bent so that it is taking the fastest path possible. Refractive index happens just because the dense medium slows down the light. And so it turns out it's like if you're moving through a dense medium and then you have a place to get to that has one dense medium that you move through and one not dense medium that you move through. The best example is what we have right here. Let's say that you're out hiking and you're at point A and you want to get to point B. Point A is in the snow, point B is in the grass, and so the question is, what is the fastest path from point A to point B? Well, because you move much slower through the snow, we've had a lot of experience with that this year, if you move a lot slower through the snow, you could say, maybe I just go straight from A to B. But if you look at that path, you're spending like half your time walking through the snow. And let's say that the snow is like it takes you 3 times as long to walk through it. I know that's probably what my rate is for snow relative to flat, grassy ground. And if it takes you 3 times as long, it doesn't make sense to actually spend half your time walking. It makes sense to spend less than half your time walking. So the orange line is the direct path, and that is not the fastest path because the snow is too slow. Well, on the other hand, okay, well, what if we just go from point A straight down, we try to get out of the snowy area as fast as we can, and then we turn and we walk to point B. That has the advantage of keeping the least time in the snow, but actually if you look at that, that is a much longer path. And depending on where point A and B are and where the snow is, usually that's not the fastest path either. So for this particular example, neither the orange path nor the red path are the fastest path. The fastest path is actually sort of a halfway path where you walk sort of between the red and the orange line, and you walk to a point where you maximize your speed. You know, it's not a simple solution. It's actually a curved line, and to solve curved lines, we have to use calculus. And so what you do is you actually can set up an example of a function right here, and you can say, okay, what's one variable that I can use to sort of compare my paths? And they say, well, okay, let's say that we have the displacement along the grass line x right here. Okay, so if for this orange path right here where you're just walking straight out and then you're walking to point B, we'll call that 0. And every like meter that we move more to the east here, every meter will be a unit along x. So we can actually calculate, and we can see that, you know, if our x is too big, we have the orange line and our total travel time is high. If our x is 0, we have the longest path line and our total travel time is also high. And so there's some point between the two where we have our minimum total travel time. And the thing is, this actually describes a curved line, and we can find the minimum of the curved line using calculus, because we can find, you know, the tangent to the line, we find the place where the slope is 0, all that fun stuff. You don't have to do that right now, but we're actually going to do this technique sometime later in class, so I'll bring it up again. The main thing is you can use calculus to find the minimum and to find the best x that will give you the fastest path from point A to point B. And it will be somewhere in the middle depending on how fast the snow is and how fast the grass is. What's really interesting is that this is the path that light will take. Light will actually take the fastest possible path, and the bent path that the hiker takes right here is similar to the bent path that light will take when it's passing from a dense medium to a less dense medium with a faster movement that it has. How does light know this? You know, it's some kind of weird, actually, quantum mechanical type phenomenon, because it's kind of like light being quantum mechanical can sample all of the possible paths, and the path that we see is the best / fastest path that light has. I've talked to my physics friends about it, and I've tried to have them explain it to me, and I can repeat some of the words that they have, and I still don't know exactly how can we say that light knows calculus. Well, it doesn't. It's just canceling out to the most efficient path. Whatever it is, we can use calculus to understand how light works, and the best answer is the answer that light actually takes. So, and they actually have this quote. This is a quote from a New York Times article. You can see the link at the bottom. And it says, "Nature, cue the theme from the Twilight Zone, nature somehow knows calculus." Okay? That is the yellow journalism newspaper way of talking about it. But I'm sort of intrigued by that way of looking at it. My physics friends are like, it doesn't know calculus, and I have to agree, but I think it's a kind of a cool metaphor at the very least. So, with all of this idea of refraction, the bending of light as it moves from one material to another of different refractive indices. The refraction and reflection are related because reflection is actually going to be an extreme form of refraction. If refraction is just the bending of light, and if we have like a prism next to water, you will have the light coming in like a red laser shining in, and we have an angle at which it's refracted when it moves into the water. When you reach a certain point, you see how it's sort of bent like this, right? What if you keep increasing this angle theta? So it's like this, right? And you have the interface that's flat right here. And what if you keep moving the light out right like this? Well, this will bend down. This will keep bending and bending. And at some point, you're going to bend it to the point where it actually doesn't even touch the air anymore. And if you bend it past that point, yeah, the light's still bent, but it's internally reflecting off the interface. So this is where the interface turns into a mirror. It's the point at which you've moved beyond the angle where you can't bend it, or when you bend it, it bends back into the starting medium rather than bending into the upper medium. And this is called total internal reflection. It's kind of a cool phenomenon, and it is what Biacore is actually built out of. Now, it occurs when light travels from an optically dense medium, glass prism, to a less dense medium, and water is a less dense medium than glass. And so there's a certain angle, critical angle, at which this happens. Remember that when the light is doing this, it is reflecting because it's reflecting off the water, and in a sense, it's still touching the water, right? It has to know the refractive index of the water somehow. And again, this is quantum mechanical in nature, that it can actually see the water without really going into the water, because it's totally staying in the glass the whole time. But it's reflecting off the water interface. And so it knows what the refractive index of the water is. Okay, so that is what the total internal reflection happens. And that's surface plasmon resonance. We still haven't explained any of those terms. Well, the key to Biacore is that you have total internal reflection taking place on a glass prism off a gold surface. And the reason why you use a gold surface is because the gold has a special phenomenon called plasmons in it. Now, you remember from general chemistry that gold, like all metals, is going to have a whole, all the electrons in it are not attached to particular nuclei, at least the outer ones aren't. They're all moving around, and there's like a superhighway for electrons, and they're able to move around. And they call it the electron sea, SEA, in some of my old classes. You have this ocean of electrons that's moving around inside the metal. It's one of the reasons why metals conduct electricity, because the electrons are free to move around within the whole metal. And so that's what electricity is. Well, sometimes you can get all the electrons moving together, and they move together as a single unit. So it's kind of like, instead of all the electrons moving in one direction like in a wire, sometimes the electrons are basically staying in place, but they're wiggling back and forth, and they're all doing the same thing at the same time. And there's a whole group of electrons that's all doing the same thing. That group of electrons is called a plasmon. So it's a weird electrical engineering type thing, and as a chemist, I probably am explaining it a little fuzzily, but the important thing is, as a group that has a certain motion and a certain charge and a certain location, it has a certain energy. And that energy will actually, turns out that it resonates with light wavelengths. It turns out that the energy of a group that is a plasmon, when it oscillates in metals, it's actually going to resonate. It's the same energy gap that is going to match the width of a light, or the length of a light wave. So actually, most metals do have plasmons, because, you know, this is going to happen when you have the electrons that are free to move around. But most metals are going to resonate in the UV range, which we can't see. Therefore, they reflect all visible light. And so what we see is we see a silvery color when we look at them. Silvery is actually closest to white. You know, it's like the gray of the metal, but it's white light. And it's reflecting all visible light, the whole rainbow of colors. But some metals, a few metals, are different. Gold and copper in particular, they have different energy levels for their plasmons, just from the way the electrons interact with the nuclei and things like that. And gold and copper actually have some plasmons that will absorb some of the light energy that we can see. Therefore, they're colored. And so I think that gold's yellow color is probably related to why its plasmons are good for SPR. And so the yellow color of gold is actually related to this cool chemical phenomenon, and that will actually help us build an instrument out of a prism and a gold surface and a red laser. So the electrons are moving together, right? And of course, when I thought about this, I thought about, you know, all the dancers in the halftime show that are all moving in like perfect synchronicity, right? And you can see that they're all moving together. So it's like the electrons are like the dancers right here. Beyonce and her dancers are illustrating for us what electrons oscillating together will look like, okay? So, yeah, sorry, no music. It's probably copyrighted, but we have this example of a GIF of what the electrons, you can imagine them doing it if you want to have like the Tron style imagination of what's going on here, okay? So the oscillation of a light wave matches the oscillation of the electrons. When that happens, there's resonance between the two energies, and one form of energy can be transformed into another form of energy. And energy can be transformed and transferred from one place and location to another. So this is a really cool way in which plasmons can connect light to work. Work is a particular movement in a particular direction. We're going to talk more about this in chapters 1 and 2, depending on when you're watching this. So light is a light beam, and most light that's not lasers, which are easy for us to see, but most light is not collected in a beam as much as a laser is. What's cool about plasmons is because they absorb visible light, and because they're made of electrons, the light is pushing the electrons around, in a sense. And the light can push the electrons in a particular direction. That means movement in a particular direction is the definition of work. Once you have a force applied over a distance, you have work rather than heat. And once you have work, you can do all sorts of things. Work is a very special case. And so light hitting something and getting hot is easy. Light hitting something and doing work is hard. And that's what's really cool about plasmons, because light can hit them and it can do work. So using gold or something like that, and using a wavelength that will be absorbed by the metal, you can use the plasmons to drive reactions and to make things happen. Here's a bunch of examples. Like, for example, people have used plasmonic materials with plasmons in them, and you see you have the light coming in, and then you have work coming out. You can use it to shift bonds around in a particular direction, do that kind of work. That would be catalysis. People have made these little plasmonic machines that you put in UV light and it rotates one way. You put in visible light and it rotates another way. So just by shining a light on it, you can move it one way or the other. That's really cool. You can actually use it to grow materials. You can use the plasmons as sort of seeds to grow materials out of. They have material synthesis. And then they actually even have molecular purification. Maybe you can use the local heating effect to do little tiny distilleries on a chip. So what's really cool about this, the top two examples are probably the most relevant for our class, that you can actually shine light on something and make it move in a particular direction. Light can be transformed into work through plasmons. And so because the plasmons have this, oh, and I just have to show you, here's my cats. There they are. My cats are coming and helping me. This is George, and this right here is Molly. Molly's the mommy. She didn't know I was going to pet her right there. All right. Nice little side note for you there. But, okay, back to the plasmons. The thing about this is that, well, this is kind of cool. You know, if you have a chunk of gold, it absorbs non-yellow light, and so you see the yellow light that it doesn't absorb. And it turns out that if you change the shape of the gold in a very defined kind of way, you make nanoparticles, those nanoparticles will actually interact with light in slightly different ways. That means they'll absorb different wavelengths. And so you have these things where you have little gold particles, and the different shapes of the gold particles interacting with different salts right here will turn different colors. By having them in the different environment, you'll have a slightly different plasmonic energy. By moving that energy around, you'll move the color that you see. And so you see right here, by moving the wavelength of absorbance, you can move it all around, and they can move it by making all these different shapes. Each different shape, each different halide has a different color to it. This is all coming from plasmons absorbing visible light. And it's really cool that we can kind of tune what energy the plasmons are at. Or we can be like Biacore, and we can use gold's natural plasmon absorbance. So this is the basis. Plasmons are the basis of some really cool color-changing technology. This is a very vivid example where some people have built a chemical chameleon. And sometimes people say that metaphorically, right? This reaction is like a chemical chameleon. No, this is actually a chemical chameleon. I'm going to show you. The way that it works is it has different panels on it, and the panels have all these plasmon nanoparticles, silver nanodomes that are inside it, and the silver nanodomes are silver shells around gold cores. So silver and gold have special plasmonic properties, and it turns out that if you like move silver ions around and you sort of put them onto the domes, it will change the wavelength within the visible range. So, and you can reverse this. You can just use an electric field to move the silver around, but it's all plasmons absorbing in different places because they have different environments. And so what they do is they make it this way, and at different voltages, you'll have different colors. This voltage is red, this voltage is green, this voltage is blue. Okay, that's really neat. And here's an example. They just show you the actual panels right here. And right here they have the different voltages which cause this, what they call electrode deposition down here, okay? But as you move back and forth, electrode deposition time, you move up and down in the peak wavelength, and the square changes color. So basically by changing the silver ions that you have in there, you're changing the color of it. That means if you build something out of those panels, you can have each panel change color. So what they did is they built a little chameleon model, and they put the panels on this side. On the other side, they have sensors which will detect what color is behind it. And what they did is they take this chameleon, and like if you put it down on this multicolored background up here, the parts that are green behind it, the panels will turn green. The parts that are red behind it, the panels will turn red. And they set it all up to be automatic. So this really is a literal chemical chameleon. The way that it really shows up, and you can probably find a video for this, but I think it's shown really well with just these 3 panels. You put the chameleon on a little motor, so this is your chemical chameleon robot. You have it moving past a red background, it's all red. You have it moving to a green background, and the green panels will change to green. And then you move it to a blue background, and the blue panels, the ones in front of the blue, will turn to blue. And so it's literally like one of those cartoon chameleons that's making the really weird pattern that's right behind it. Real chameleons can't really do this, I don't think, but this chemical chameleon can. This is all from electricity changing silver ions and basically changing plasmons, changing the environment of plasmons to do different things and to be different colors. So this is the only place that you'll see the word relativity this quarter. It's a part of physics that doesn't get into physical chemistry much, but it does show up here. Now when people say relativity, you kind of have these, it's one of those big science words that's really weird, but trust me, it's really cool if you get into it. Dr. Lindbergh does a great talk about relativity that I encourage you, if you haven't had him in Capstone, to seek out that talk, even slip in the back for the day, because he will explain relativity to you. I'm not going to try, but I'm just going to say it's the same thing that Einstein said, and it takes place only when you get near the speed of light. Therefore, as a chemist, I'm like, well, I'm never moving near the speed of light. Why do I need to know anything about relativity? And for the most part, I don't. But the fact of the matter is, there's actually some cases where electrons can be naturally moving near the speed of light. There's a whole review right here, and I have the reference down here, if you're interested, that talks about things in chemistry that might be affected by relativity, and one of them is gold's yellow color. Why is gold different from silver? Silver reflects all visible light. Gold reflects, why are its plasmons in the energy range where they actually will absorb visible light? Well, one of the things that's interesting about gold is it's also on the bottom of the periodic table, right? And because of it's on the bottom, it has a really big nucleus. And the electrons that are really close to the nucleus, like the 1s, 2s electrons, are actually going to be really confined and really pulled on by those huge positive charges. Remember, though, they're not going around in circles like this, right? They're in clouds like that. And so they're spending a lot of time close to the nucleus. That means that they experience a huge acceleration from all the charges of the nucleus that are right there. And if you calculate what that acceleration is going to be, from time to time, it's going to actually, on average, be a substantial fraction of the speed of light. It only has to be 10–20% for relativistic effects to start to happen. And so there's good evidence and good reason for thinking that the reason why gold is yellow, its electrons are special, because its nucleus is so big that it's accelerating the electrons close to the speed of light, and that changes their apparent mass, it changes their speed, their acceleration, and all sorts of weird things happen. So I think that that's true, and you can look at the review if you want to know more. There's also, right next to gold, you have lead, another big nucleus, and it looks like lead has special weird effects that we don't expect it to have from its place on the periodic table. Well, that also appears to be because it has electrons that are accelerated to near the speed of light. Okay? So lead is used in car batteries because it has special electrochemical properties. We're going to talk about those when we get to Chapter 5. But special properties are made possible by relativity. There's another paper that proves that. So relativity makes gold yellow, it makes lead good for batteries, and there's probably a number of other things that it does as well that people are figuring out. So the light energy hits the gold, and it sets up plasmons, especially on the surface of the gold where the light is hitting the gold, right? Those surface plasmons can move electrons and do work. Here's an example in a solar cell where you have a gold nanoparticle, photons hit the gold, they interact with surface plasmons, and that changes the oscillation of the plasmons. The energy gets transformed, and the energy can be transformed into the electrons moving in one particular direction. The electrons moving like this. And that is work. So the light energy hits the gold, is changed into work. And that is a really cool thing that we can do a lot with. So The way that this all works is that you have the total internal reflection happening in the prism. You have a red laser, and I believe the red laser happens because it's close to what's being absorbed by the gold. You don't see red when you look at gold because it's being absorbed by the surface photons, or the surface plasmons. And so you have a total internal reflection of the red laser at the right angle, and it hits the gold, reflects off, but remember that it's sampling sort of the water a little bit because it knows the refractive index of the water. It says right here light energy is lost to the gold electrons, which oscillate to form surface plasmons, okay? And the resonance happens when the momentum of the photons coming in is equal to the momentum of the plasmons on the surface. That's visible wavelength. We can use a red laser, and that's why we need to use gold. So you actually have this angle right here. That's called the SPR angle, because actually, even though a laser is really tight, the prism is still separating it out slightly. So you have a bunch of angles within the gold light coming out. There's one particular angle where you're going to have the resonance, where the energies are just right, and the wavelength of the light is just right to resonate with the surface plasmons of the gold. To resonate with the surface plasmons also requires the interaction with the water's refractive index, because remember, it's bouncing off of the water. So you've got three things going on here, really four. You've got the laser, you've got the prism, you've got the gold, and you've got the water, okay? Resonance happens when these all line up so that the energy is transferred into the plasmons. It's absorbed by the gold. Now it says light energy is lost. Okay, I think that's a bit, that's what I got the slide from, but that is not entirely accurate. Energy is never really lost. Maybe light energy is lost, but other energy is gained. And it's changed, it's transformed to other forms of energy when it matches plasmon energy levels. The main thing is the light is definitely changed away from light energy. The light energy is not there anymore. When you look for it, you have a particular angle that you see a shadow. The shadow happens because of the refractive index of the water behind the gold. And so that's a whole bunch of stuff. And so you can probably see why the Biacore people don't want to take the time to spend half an hour teaching you what plasmons are and how they work. But now, because you're in a physical chemistry class, we can take the time, and we just did. Though, if you think about it, this resonance is a quantum mechanical effect. The light is bouncing off of the gold surface, but it's also sampling the water. It has to sample the water because the refractive index of the water determines whether it's reflecting or not. So when the light bounces off the water, the way they explain this is there's this quantum mechanical phenomenon called an evanescent wave, which is actually kind of a cool name. Physics gets all the cool names, I guess. But there's an evanescent wave that the light is sort of quantum mechanically there and not there at the same time. It's how the light knows what the refractive index of the water is. And it will know what the refractive index of the water is. It sort of quantum mechanically walks through the wall. And we know exactly what this evanescent wave is. It's not really spooky. We can calculate exactly what it is from the uncertainty principle. And the depth is 1/2 of the wavelength. And so that tells you right there, the wavelength of red light is right around 400 to 500 nanometers. So that means that the depth to which the light is sampling of the surface is only about 200 nanometers in width. It's a very small width, but that does include a range that if we have something on the surface, we'll be able to see it. So the light sets up an evanescent wave, and the light will resonate with the plasmons on the opposite surface of the metal. The gold has to be very thin. It's another reason why we use gold and not copper, because gold can be made extremely thin. And gold can be made, I believe it's thinner than the wavelength that we're dealing with. So because the light is a wave, it's quantum mechanical, it's delocalized, it extends into the water solvent on the other side of the gold surface. And so it's somehow able to see through walls. And that's just another cool thing of physics. Okay? There's the evanescent wave that they're showing you. That is what they're talking about being set up at the surface and extending into the water on the other side. There's the surface plasmons. So the wave is affected by the refractive index of the solvent on the other side because of total internal reflection. And the refractive index of the solvent on the other side is changed by the mass. Something that is thicker will tend to have a higher refractive index. So if we've got some stuff on the other side of the wall in the water, it's actually going to change the energy of resonance, and different wavelengths of light will be absorbed. That is why we're talking about surface plasmon resonance. You have plasmons on the surface. They're resonating with the prism wavelengths of the laser light. They're resonating with a particular wavelength, and it creates a shadow. So this is another way of showing it. This is the same thing that we showed before, but I like to show it in a couple of different ways so that you can see it a couple different ways. You have the light coming in, the light coming out. There's a shadow in the light coming out, and that is where it resonates with the plasmons on the gold surface. And the response, and basically, there's a certain number of angles. If you change the refractive index down here, it will change the angle of shadowing up here. And so if you change the angle of reflection, if you change the angle of, or if you change the refractive index, it will change the angle of resonance and the angle of reflection with this prism setup. And so that means that you can just set up a detector up here, and the detector can just measure the angles of light, and it can look for the shadow. When you change the refractive index, the shadow will move up or down. And that angle change BIAcore measures it as response units. It's a very vague term, and it doesn't really have units because it's a sort of vague term. It wouldn't make sense. It would confuse people if you measured it in terms of angles. And so they just call the angle a response unit. Okay? And that is how BIAcore works. That's the inside of the BIAcore that you never really see, but it helps you to interpret the data. So that's part one. And part two, we will move on to ask, how does this work itself out in real life?